Today's video will be about the law of cosines. As we can see here, we have our formula. C squared equals a squared plus b squared minus 2ab cosine of c. But what does that mean? Well, let's draw a triangle. And there's really no specifications on what this triangle is. And we will label this vertex C, this vertex A, and this vertex B. And as is custom, we label the vertices with capital letters and then their corresponding side lengths with lowercase letters. So this one will be a lowercase c, this side will be a lowercase a, and this side will be a lowercase b. And there we have it. This formula that we have right here, c squared equals a squared plus b squared minus 2ab cosine of c, is referring to a triangle where the side lengths are the lowercase letters a, b, and c, and the vertices are the corresponding capital letters a, b, and c. So can we use this triangle and demonstrate that this formula does indeed hold? Well, let's see. So we can draw a vertical line here in the point that this becomes a right angle. And let's define a new point right here. Let's define this point D. And we still remember that this side length is B, but just for space reasons, I'll just keep this as D. And remember, it's a capital letter, so it's referring to a point, not a side length. Let's consider the cosine of C, right? And this is the cosine of our capital C here. And it makes sense to consider this since when we see our formula, we have a cosine of C. So let's try it. Well, now that we have a right triangle, right, formed by this side segment CD, this side segment DB, and then our side length A as our hypotenuse, we know that the cosine of C is the adjacent, which in this case will be the line segment CD, where since these are capital letters, this will refer to a line segment. And then we divide that by the hypotenuse, which is A. Now we can multiply by A on both sides, so we have A times cosine of our capital C is equal to CD, right? However, we note, right, that this side segment, CD, plus our side segment, DA, is equal to B, which we can demonstrate here. So we have CD plus DA is equal to B. However, because our CD is equal to A cosine C, we have A times the cosine of C plus dA is equal to B. And if we want just dA by itself, what we can do is we can say we want dA is equal to B minus A cosine of C. Similarly, we can ask ourselves, what is the sine of C? So we write sine of this angle, right, determined by our vertex C. And we look at a right triangle. Sine is going to be the opposite over the hypotenuse, where in this case, this opposite is this vertical line we constructed. This BD divided by A. We multiply by A on both sides. We get A times sine of C is equal to BD. And therefore, we have that as our line segment. Now, we can look at this triangle on the right. So we have BDA. And we can use the Pythagorean theorem to relate our hypotenuse C to the legs of the triangle. So what does that look like? We say that C squared is equal to BD squared plus dA squared. So we notice that because we have a formula for BD and we have a formula for dA, which I wrote over here. We can make a substitution as follows. So here I have rewritten our formula, and I've substituted it in. So now we can expand the squares and try to simplify some things here. So we have c squared is equal to a squared sine squared c plus b squared plus a squared cosine squared c minus 2ab cosine of c. And already we can see that this is starting to look like the answer that we want to get. So what can we do? We can simplify this even further. We say c squared is equal to a squared times sine squared c plus cosine squared c plus b squared minus 2ab cosine of c. Now, of course, this quantity right here is equal to 1 because of the Pythagorean identity. So we have a squared times 1 plus b squared minus 2ab times cosine of c. And therefore, we can see that starting from this triangle, we have the side length c is equal to the side length a squared plus the side length b squared minus 2ab cosine of c, where in this case, this c is referring to the vertex. And this demonstrates the law of cosines.